Let's next look at refraction and how it relates to Snell's law. So, a ray of light shines from a lighthouse into the ocean at an angle of 25 degrees with respect to the normal of the water. So let's draw this up. So let's say that this is our water, and here we have air, and then water, and then a ray is shining down like this. And the normal is a perpendicular line to the surface of the water, and an angle of 25 degrees is made, like that. And our question is, what is the angle that the ray enters with on the side of the water with respect to the normal? Okay, so we're looking at what is going to be this angle. Okay, but first, let's think about this conceptually. Let's think about how the ray of light is going to be refracted. So the index of refraction for air is about 1, and the index of refraction for water is about 1.33. So we're going from a medium that is less optically dense at 1 to a medium that is more optically dense at 1.33. So when we go from n low to n high, just another way of writing it. The refracted ray, so the ray that will now be in the water, will bend. So this is the important part. Which way will it bend? Will it bend towards the normal or away from the normal? And the answer is that it will bend towards the normal. And this is important to keep in mind for later problems. So it will bend towards the normal, like that, rather than being directly transmitted. Okay? So in that case, let's keep solving the problem. We're going to have to use Snell's law. So from the medium that you started, which is air, we have n1, so the n of air, times sine of theta 1, the angle in the air, equals n2 for water, times sine of theta 2, which is what we're trying to figure out. Okay? So in that case, we just have to rearrange this to figure out what theta 2 is. So we can divide by n2 on each side. Okay, so we have sine theta 2 equals n1 over n2 times sine theta 1. Okay, and then to get rid of this sign, we can just take the sine inverse. So sine inverse of this whole term, n1 over n2 times sine of theta 1. Okay, so now that we have our equation arranged, let's plug in what we need. So n1 is where you're starting from, so air. So 1 divided by n2 is where you end up, so water, 1.33, times sine of theta 1, which is the angle between the normal and the ray, so 25 degrees. Okay, so let's see what our calculator gives us when we plug this in. So sine of 25 divided by 1.33, and then the sine inverse of that value. So I get 18.5 degrees. Okay, so now it's important, does this answer make sense? So based off of our rule here that the ray should refract towards the normal, yes, it does make sense. So 18.5 degrees is less than the 25 degrees. So everything checks out. Okay, continuing this, what is the angle on the air side for a ray of light from a bioluminescent fish that forms an angle of 40 degrees with respect to the normal of the water? Okay, so let's draw this then. So let's say that is our water. Here's our normal. And here's our fish. And it shines a ray of light like that makes a 40-degree angle with the normal. Okay? So now, what is the angle of refracted light on the air side? So if before we went from a low dense medium to a high dense medium, what will we think will happen in reverse? So now we're going from water, which is 1.33, to air, which is just 1. We're going from high to low. So N high to N low. Basically, it's just the other way around. So before, the light ray that was refracted bent toward the normal. Now it will bend away from the normal. So away from normal. Okay? And it will look like this. So we're bending away. And then theta 2 will have to be bigger than 40. So let's see if this checks out using Snell's law. So this time, we're still going to use N1 sine theta 1 equals N2 sine theta 2. But N1 will be the N for water, index of refraction for water, because that's where we're starting, times sine theta 1, which is the 40 degrees, equals N2, which is air, so just 1, times sine of theta 2, which is what we're trying to figure out. So we're going to end up with theta 2 equals sine inverse of N1 divided by N2 times sine theta 1. Okay, so let's plug everything in that we know. Theta 2 equals the sine inverse of N1, so this time 1.33, divided by 1 times sine of theta 1, which is 40 degrees. Okay, and let's see what our calculator gives us. So sine of 40 times 1.33 and sine inverse of that value. So we get 58.75 degrees. Okay, so in that case, it does make sense. It lines up with a rule that the refracted ray bent away from the normal. Okay? So with this in mind, there's something kind of cool that happens, and it's that we can figure out what the critical angle is. So for the water to air interface that we've been using, let's figure out what the critical angle is. And I'll explain what a critical angle is in just a minute. So if this is water, and this is air, and this is our perpendicular normal, something that happens is when you have light coming from water, so coming from a dense medium to a less dense medium, eventually it will jut out along the surface of the water like that, and it will make a 90-degree angle. And when that happens, this angle right here is called the critical angle. So if we think about it, it's actually not too complicated to figure out how to find it because we have this 90-degree angle. So using Snell's law, take N1 sine theta c, so where we're coming from, equals N2, the less dense medium that we're going to, times sine of 90 degrees. And this is really the important part. Whenever you're finding a critical angle, that theta 2 will always be 90 degrees, because that's what the critical angle actually means. So in that case, the value for sine of 90 is just 1. Okay? So let's rearrange this to find theta c. So the critical angle equals sine inverse of n2 over n1. Okay? So let's plug this in. Sine inverse of n2, so where we end up is in air, divided by n1, which is where we came from. Okay? So the calculator tells us 1 divided by 1.33 and sine inverse of that value. So we get 48.8 degrees. Okay. So thinking about this now, let's redraw it. So if our ray coming in is at that critical angle of 48.8 degrees, normally it'll jet out like that right along the surface of the water. What happens if we exceed this angle, this critical angle? So let's say theta 1 is greater than theta c. So just something to think about. If now we say we change it to be 50 degrees, instead of escaping and jutting out along the surface like this, it will now be reflected, just like that. So instead of being refracted out into the next medium, if you exceed the critical angle, it'll just be reflected back down. Okay? And I said that this is 50 degrees because of the law of reflection, where the incident angle is the reflected angle. Okay? And still thinking about the same subject, is there a critical angle for an air to water interface? So instead of coming from water and going to air, how about we flip it where we go from air to water? So let's draw this. So now, is there ever a time where you start in air, you go to water, where this angle will ever be totally reflected? And the answer is no, because of our rule up here, that the refracted ray will bend towards the normal. Okay, so no matter what angle you draw this at, it will always be refracted towards the normal.